In this problem, we're going to look at the following 2x2 matrices and how they act on two-dimensional space in terms of a linear transformation. So we're going to draw a picture to show AE1, AE2, and AB, where E1 and E2 are the standard basis vectors, and B happens to be the vector 2 times E1 plus 3E2. And we're going to do it for 3 different examples of A. Okay, so this is a very useful thing to be able to visualize how a 2x2 matrix affects a linear transformation. So let's have a look at the first one. We have the matrix A, which is 2, 0, 0, 0.7. So along the diagonal, we have the numbers 2s. So along the diagonal, we have the numbers 2 and 0.7. Right, so what happens to the various vectors? We'll make a computation down here. So A of E1 will be taking the matrix 2, 0, 0, 0.7, and we're multiplying it by the vector 1, 0. That's what E1 is. When we do that, we get just 2, 0, namely the first column. If we do the same thing with the second basis vector, AE2, then we get 2, 0, 0, 0.7 times 0, 1. That's the second basis vector, E2. And when we do that multiplication, we get the second basis vector, which is 0, 0.7. And maybe over here, we'll do what happens when we take A times B. Okay, so that means we're taking the matrix 2, 0, 0, 0.7 and multiplying by B, which is the vector 2, 3, because it's 2 times the first basis vector plus 3 times the second one. When we do that multiplication, we get the vector 2 times 2 plus 0 times 3 for a total of 4, and 2 times 0 plus 3 times 0.7, which is 2.1. So we can now visualize where all these things are. Let's draw them on the diagram. So A of E1 is 2, 0. I'll draw it in red. So there's A of E1. So this transformation has stretched things in the x direction by a factor of 2. And A of E2 is 0, 0.7. It's a vector in this direction, just a little bit up like that. So there is A of E2. We see that this linear transformation has dilated things, shrunk them by a factor of 0.7 in this direction. And what's happened to B? Well, B has gone to the point 4, 2.1. So if you go over 4, 1, 2, 3, 4 over here, and 2.1 up to about there. So the net effect is something like this. There is A times the vector B. So the net effect of dilating by a factor of 2 in this direction, at the same time contracting by a factor of 0.7 in the y direction, sends this vector B to that vector over there. All right, let's have a look at the same situation here, but we'll just sort of write down some things. So let's compute that A times E1. A simpler way of doing this is just to observe that that's going to be the first column, minus 2, 0, while A of E2 is the second column, which is 0, minus 3. Finding the effect on B is a bit more challenging, so we'll do that over here, say. So we get the matrix minus 2, 0, 0, minus 3, and we're going to multiply by the vector 2, 3. Which gives a total of minus 4 and minus 9. Okay, so where is all of that? A of E1 is vector minus 2, 0. So this vector over here is sent to minus 2, 0. There's A of E1. A of E2 is 0, minus 3, which is down here. There's A of E2. So on the basis vectors, we see that this transformation is dilation, but a dilation of a factor of minus 2 in the x direction and a factor of minus 3 in the y direction. And what happens to our vector b? Well, it gets sent to -4, -9, which is probably a little bit off our page, down here somewhere. There would be the vector a, b. -4, -9, that's the vector there. And that sort of makes sense. We're taking this vector b, which is in this direction. Its component in this direction is being negated by a factor of 2, and the component in this direction negated by a factor of 3. And our third example, we have a more complicated matrix, the matrix 4, -4, 3, -4. So let's first of all figure out what happens to the basis vectors. E1 gets sent to the first column. That's how you easily read off what happens to the first basis vector. And AE2, that's what's going to be the second column, which is -4, -4. Let's plot those first to see where we are. So here I'm using a slightly smaller scale because I can see that there are some numbers here that mean that we're going to be scaling upwards, so I need more room. Okay, so here is E1, and where is A of E1? It's vector 4, 3, it's right here. So there's A of E1. And A of E2 is -4, -4. -4 and -4, it would be down there. There's A of E2. Not quite along the same line. This is a little bit tilted over. And finally, what happens to our matrix when we apply it to our vector 2, 3, vector b here? Well, the matrix multiplication is 4 times 2, which is 12. Well, the matrix multiplication is 4 times 2, which is 8, minus 12, which is -4. And second entry, 3 times 2, which is 6, minus 12 is -6. And that is the vector, -4 this way and -6 there, sort of along the same lines, but over there, so there's A times the vector B. And so there's a visualization of the action of 3 different matrices.